There we go. Okay, so if you run across an argument in the real world, so maybe you're reading a book or you're arguing with a friend or something like that, your argument is going to end up looking something like this. So most real world arguments are structured something like this. They won't be organized maybe exactly the same way because, well, maybe you're writing a paragraph instead of lines, or you're having a conversation instead of writing. So it might end up looking different, but the structure is something like this. And this is a silly argument. If it's raining, then there must be a cloud above me. It's raining, therefore there's a cloud above me. So it's a very simple argument. Probably you've made one similar to this, or you've seen arguments like this written down. And we'll come back to this particular argument in a second, but for now I want to give some of these things names. This process of drawing conclusions, so this last line was my conclusion. This is called deductive reasoning. So if you deduce something, that means that you're using logic to draw a conclusion. So this kind of formal logic that we've been doing. And then something like this, an argument. Well, most of the time we're interested if we have a good argument, right? So there's a name for a good argument, and it's valid. So an argument is valid if the conclusion, so the end of our argument, what we're trying to argue for, is guaranteed to be true by the hypotheses. So the first part of the argument. Or you might call these premises or premises. That's this first part. Let's see. I should point out that the way that we use this word hypothesis is a little bit different than the way that you might have seen it used in like a science class. So in the scientific method, a hypothesis is something like a guess. And then you use observation to determine whether your hypothesis, your guess, is actually true or not. Or mostly you're trying to determine if it's false, but that's beside the point. In logic, the hypotheses are a little bit different. They're more like the basis for your argument. So they're like the underlying ideas. So keep that in mind. We're using this word a little bit differently. So in deductive reasoning, we're trying to see whether our hypotheses guarantee that our conclusion is true. Whereas in science, you might use an experiment to determine if your guess is true, your hypothesis. It's kind of backwards, almost. So this is kind of how reasoning works in arguments. And what we want to do in this section is link it back to the more formal logic that we've been doing, because we want to be able to determine for sure, without a shadow of a doubt, whether an argument is valid. And math is the way that we do that most of the time. And when we're doing logic and math, we have the notation like we've been using. So we use letters for propositions. And in an argument, you often have many propositions. So up here in the example, each of the hypotheses is a separate proposition, and the conclusion is its own proposition, something that's true or false. So we could have lots of hypotheses. That's what these letters are going to represent. And my conclusion I'm going to call Q. Oops. I'm not sure if you've ever done this before, but if you try to talk and write at the same time, sometimes you end up writing what you're saying instead of writing what you should be writing. So for this, the conclusion and the hypotheses is flipped for deductive reasoning. It's flipped compared to the way that you would think about the scientific method. So in the scientific method, the hypothesis is your guess, and you're trying to determine whether your guess is false or not. And so that's why it's a little bit backwards. Okay, so what am I going to do with all of these propositions? Well, I'm going to structure them into an argument. And the way that we like to do this in the more abstract logic setting is by stacking all of our hypotheses on top of each other, like this. And then we draw a horizontal line, put 3 little dots arranged in a triangle, and then the conclusion. And let me just label that. I kind of said this as I was writing it. So these are your hypotheses. Or premises. Both of these words mean the same thing. And Q here is your conclusion. And the symbol, the 3 dots arranged in a triangle, is standing in for the word therefore. So this is the symbol for the word therefore in English. So this whole thing, the stack of hypotheses on top of your conclusion, this whole thing is an argument. So you're saying that whatever you wrote here justifies your conclusion. Just like the way that I structured the silly little argument at the top, I have my hypotheses, and then I say, therefore, my conclusion must be true. So it's the same structure, but we might want to use symbols like I did here instead of writing out whole sentences all the time. Are there any questions before we go on to the next page? Okay. So let's move on to this example. Or actually, we're really just continuing our first example. And what I want to do is consider the structure of this argument. So the first proposition says, if it's raining, then there must be a cloud above me. And what I can do is I can label these. So it's raining can be one simple proposition, and then there must be a cloud above me could be another one. Maybe I'll label that one Q. And then we can look at the rest of them. It's raining, that was my first proposition, P. And then, therefore, there's a cloud above me. That was the conclusion, Q. Let me write some of this on the next page. So P, I'm saying, is the proposition, it's raining. And Q is the proposition, there must be a cloud above me. Or there is a cloud above me. And then instead of writing out the sentences like I did here, we can use our symbols to make the same structure, the same kind of argument. So the first line, the first proposition was the conditional. If P, then Q. If it's raining, then there must be a cloud above me. The second hypothesis was just P by itself. It's raining. So I would, on my next line, write P. There we go. And then the conclusion is that Q must be true, that there's a cloud above me. So this original argument, the example, actually looks like this if you use symbols. So this is the first example in symbolic form. And the reason that you might want to rewrite your argument using symbols is that, well, there's lots of arguments that have this exact same structure. If P, then Q, P, therefore Q. And they could be quite different from the silly argument. Maybe they're more interesting or more important somehow. But I don't want to have to check every single time I see this kind of argument whether it's valid or not. So that's why we rewrite it using symbols and then determine if this kind of symbolic argument is valid. So if it's always true. Is this just a different way to write? It's a little bit different. So an argument isn't a single proposition. Like I said earlier, what an argument is trying to do is say that if these two hypotheses are true, or if however many hypotheses you have are true, then your conclusion must also be true. And we're going to see in just a second how this relates back to truth tables. In fact, right now, we're going to do that. So what I want to do is determine if this argument is valid. And remember, valid has a very specific meaning in logic. So valid means if these are true, then the conclusion must be true. So it's a little bit more specific than the way that you might use valid in everyday speaking. So what I need to do is make a truth table with my simple propositions P and Q, and then I want to add columns for each of the hypotheses and the conclusion. So I'll make a column for the conditional, if P then Q. I'll make a third column for P, and then a fourth column for Q. So these are my hypotheses. Each one gets a column. And this is my conclusion. And in case you're wondering why I put these extra columns here for P and Q, even though we're already going to have them, it's because a lot of the time when you have symbolic arguments like this, you will have things that are more complicated. And you always want to include these columns just for good practice for when it comes to those more complicated kinds of propositions in your argument. So now that we have our truth table with our hypotheses and our conclusion, we just fill it in exactly like we would a normal truth table. So you have 4 rows with 2 simple propositions. So the different combinations of true and false. And then you just work to the right like normal. So if P then Q, remember, is only false this one time when P is true but Q is false. And then for these 2 columns, I'm just going to fill in their truth values. This is a relatively simple argument, so I don't have to do any extra work for these columns. But if it was a more complicated argument, you might have to do a little bit more work here. So with this truth table, what I'm going to do now is check to see if the argument is valid. And by that, I mean, I have to check that the conclusion is true whenever both of the hypotheses or all of the hypotheses are also true. So that's what we mean by valid. If the hypotheses are true, the conclusion must be true. So which rows correspond to the 2 hypotheses being true? So we need a true for if P then Q and a true for P, excuse me. That's actually only this one row here. In these other 3 rows, you can see that there's at least one false in the hypotheses. So this is the only one that matters for this particular argument. And we can see, right, Davian. So we can see that when both of these are true, the conclusion Q is true. So this checks out. The argument is valid. Okay, so are there any questions so far? Just need more examples. Yeah, we'll talk through a few more in the next few minutes. Maybe I'll leave it there in case anyone is writing for just a few more seconds. Okay, so that brings us to the next little topic here called the rules of inference. So what these are brief, valid arguments that are building blocks for more complicated arguments, essentially. So they're brief, valid arguments that are commonly used. Often as part of a larger argument. And these so-called rules of inference, they go back a long time. And we're going to see in a second that they go back at least as far as like the Romans, and some of them have Latin names attached to them, because people have been thinking about logic and arguments for a very long time. So the first rule of inference is called modus ponens, and it's the one that we just did. It's the argument says, if P then Q, P, therefore Q. And we actually already showed that this one is valid. It's the one that we just did. So every time you see this structure used, it's always going to give you a valid argument. And one thing that I want to point out in logic is that often you'll see people arguing, and both of the people arguing will have valid arguments. Let me explain that a little bit better. So maybe in disagreements, let's say, maybe you're arguing with your friend about something. So often both sides actually do have valid arguments. But remember that a valid argument is a very specific kind of thing. It means that if the hypotheses are true, then the conclusion must be true. So even though both sides, they disagree with each other and they both have valid arguments, the real problem comes in the hypothesis. So usually in these kinds of cases, the real disagreement is over the hypotheses. Because you can make really totally nonsense arguments that are totally valid. And we can just use this particular structure to show that's true. We can just put in nonsense words. So if blurg, then blarg. blurg, therefore blarg. So it totally has the right structure. If P, then Q, P, therefore Q. So it's a valid argument, but it's complete nonsense. Because the hypotheses don't make any sense. These parts that support your conclusion, well, they don't really do anything of the sort because they're nonsense. So this is a kind of silly example to demonstrate that sometimes if you have bad hypotheses, your conclusion can be totally ridiculous. And that's the sort of thing that you see in real arguments as well. I'm sure you'll see some in the homework problems. I guess before I move on, are there any questions? Okay, so the next thing I want to do, since it doesn't seem like we have any more questions over that, is just go through the list of standard rules of inference. We've already met the first one, called modus ponens. It says, if P, then Q, P, therefore Q. So this is a basic kind of conditional argument. Modus tollens, the next one, is similar. It starts the same way. If P, then Q. But the next row has not Q. And the conclusion is not P. So it almost looks like we reversed these. So I switched P and Q and I put negations on everything. Hopefully that rings a bell from last time, because this relates to the contrapositive. So that was this one. So we won't make a truth table for any more of these, though I think they are on your homework, or at least you'll have to think about them on your homework. Let's just keep going. The addition rule, if we start with a single true proposition, true hypothesis, then we can use the or, the conjunction, to add more. So P, therefore P or Q. We're not really adding anything new because we're using the disjunction, the or statement. So this is a way to add extra things on. You can also subtract things off of and statements. So if I know that both P and Q are true, well, I know that P is true and Q is true. I kind of just reset the same thing. So I can drop one of them. If P and Q are true, then definitely P is true. And if I have two true hypotheses, I'm allowed to smash them together. So if P and Q are true hypotheses, then I can conclude that P and Q. The next one gets another one of those Latin kinds of names. This one's the hypothetical syllogism. And it actually relates to conditional statements. If P, then Q. If Q, then R. Therefore, if P, then R. So basically, for this one, we could look at a truth table, but essentially what's happening is that we're following the arrow. So P goes to Q, which points to R. So I could follow the arrow the whole way directly from P to R. That's kind of what's going on here, symbolically at least. And we'll see some examples of these on the next page, how they could actually look in English. And the next one, the disjunctive syllogism, well, it involves a disjunction, an or statement. So this one says that P or Q is true, and then P is false, so not P. And we know if this P or Q is true, but the first one, P, is false, then the second argument, the second proposition must be true. So therefore, Q. And if anyone is wondering what the word syllogism means, it means an argument with two hypotheses. So it's a really old word that you won't see very often unless you're doing logic. Okay, and we have 3 minutes left, which is enough time to do, I think, one example where this could actually happen, where you might actually run across one of these rules of inference. And here's my first example. If it's my birthday, then I get to pick the restaurant. If I get to pick the restaurant, then I will pick a sushi restaurant. I'll pick sushi. Therefore, if it's my birthday, then I will pick sushi. So let's look at the structure of this thing, because it has several parts. The first one, just starting at the beginning, we'll label this one, it's my birthday, P. So let me come down here. So P is, it's my birthday. Okay. Then the next piece of this is I get to pick the restaurant. Let's label that one Q. Okay, and then that part gets repeated. I get to pick the restaurant again. So the next one is actually going to be this. I will pick sushi. Okay, and then the last sentence has P, then R. So the structure here is P, or if P, then Q. So if it's my birthday, then I get to pick the restaurant. Symbolically, that's this conditional statement. The second sentence says, if I get to pick the restaurant, that's Q, then I will pick sushi, that's R. So the second one corresponds to this symbolic argument, if Q, then R. And now the last sentence starts with therefore. That signals to us that this is going to be the conclusion. And then the statement says, if it's my birthday, all of these will have PQR. It's totally up to you which letters you use. In logic, if you're reading like a logic book or a textbook that has logic, most of the time when you're dealing with propositions, you're going to start with P, lowercase p, and then just go alphabetically. So P, Q, R, and then you would go S, T, U, V, etc. if you need more. And then to finish this off, if it's my birthday, that's P, then I will pick sushi, that's R. So it's P, then R. And you should recognize this one from the list of our valid arguments. This is the hypothetical syllogism, so probably the one that seemed the most abstract is actually here. And I'm sure you've made similar kinds of statements to this. So these do actually show up, even if they feel a little foreign. Okay, and that looks like it's our stopping point for today. Are there any questions here at the end of class?